Okay, we want to talk a little bit about adding rational functions, rational expressions, because we're leading up to the whole theory of rational functions, how you graph them, how you interpret the graphs, and so forth. I'm going to show you a little bit about that starting over here. Here, and I apologize, I was doing the video as we were doing class, and I'd done one quick video at the beginning. I went over and turned off the camera, and I stopped the recording and started the next recording. I started the next recording too quickly, so it didn't start recording. So I've got to do this just by pointing at the board. I'd rather have it done live, but this might be a little shorter. Okay, so we've got x minus 4 over x plus 6. We want to add the x plus 3 over x minus 5. Just like we do when we add fractions with numbers or just single symbols, we find a common denominator. We can always use the product of the two denominators. Sometimes we can use a smaller common denominator, a least common denominator. If the two denominators have a common factor, we don't have to include that factor twice. And that's something we'll see when it comes up. But right now, this has no factor common with this one. So the common denominator is going to be x plus 6 over x minus 5. In order to change the form of these two expressions to where they have the same denominator, we multiply each one by 1. Okay, to get the x plus 6 times x minus 5 in the denominator, we need to multiply the denominator by x minus 5. That would change the value of this rational expression. However, if we multiply by x minus 5 over x minus 5, it only changes the form, it doesn't change the value, because we're multiplying by 1. Okay, over here, we multiply x plus 3 over x minus 5. We want to get this denominator. We're going to have to multiply the denominator by x plus 6, which means we'd better multiply the numerator by x plus 6 if we don't want to change the value of this expression. Having done that, well, we can multiply the numerators. X minus 4 times x minus 5 is x squared minus 9x plus 20. X plus 3 times x plus 6 is x squared plus 9x plus 18. Now the denominator will be x plus 6 times x minus 5 in both cases, so that now we can add the numerators. There's something I said earlier, I guess I'm going to have to redo that earlier video as well. But anyhow, we can add the numerators and keep the same denominator. There's a very simple reason for that I'll do in another video that will have preceded this one. Okay, so we add the numerators. We get this numerator, we get this numerator. We add them together. We're going to get 2x squared, negative 9x and 9x. Coincidentally, I didn't plan it that way, but it turns out to be 0. And 20 and 18 is 38. It's a bad looking 8, but that is 38. Okay, then I go ahead and factor, because I want to factor my numerator. But the only thing we can do to factor is factor out the 2. I get 2 times the quantity x squared plus 19. And now I note that x squared plus 19 doesn't factor anymore. And this shows me that my numerator and my denominator don't have any common factors, because if they did, I'd want to divide them out. That's why we keep the denominator factored, and then we look at the numerator to see if it factors, so we can match up any factor of the numerator that matches a factor of the denominator. Okay, doesn't happen here, so here's our final form. Okay, so that's it. That's how you would at least add two rational expressions with linear numerator and denominator, and it's easy to adapt if the numerator and denominator are a little more complicated. The idea is identical to the idea you use when you had just regular fractions. Okay? Now I want to move on and talk a little bit about graphing rational functions. Now I hate that I don't have the video because we constructed this one step at a time, but I'm going to point it out anyway. Okay, we want to graph, let's say this first fraction, x minus 4 over x plus 6. We want to graph that function. So we're going to let y equal x minus 4 over x plus 6. I should have said y equals that, but I'll say, okay, that's our y. To graph it, the first thing we want to do is find the zeros. When does x minus 4 over x plus 6 equal 0? Well, let's set that up as an equation. We multiply both sides by x plus 6. We have x plus 6 times 0 over here, and we have x plus 6, which should have had parentheses around it, times this quantity over here. X plus 6, that we can rearrange this. We get the x plus 6 over x plus 6 times x minus 4. X plus 6 over x plus 6 is 1. 1 times x minus 4 is x minus 4. So we get x minus 4 equals, well, anything times 0 is 0, so it's going to equal 0. So x equals 4. We conclude that when x equals 4, this fraction equals 0. And that's going to give us this point on a graph of y versus x, because y equals 0 when x equals 4. This is the point 4, 0. And I could have written that. I could have written the coordinates, but I didn't. So I'm going to leave it the way it is. We understand then that whatever this graph does, it has to go through this point. Okay? Now, that's easy, for this function at least. Then we want to find the y-intercept. Well, the y-intercept occurs when x equals 0. So y equals x minus 4 over x plus 6 would be 0 minus 4 over 0 plus 6. That's negative 4 over 6, which reduces to negative 2/3. That's the y-coordinate when x equals 0. That's the y-intercept. Y-intercept then occurs when y is negative 2/3. There it is. So the graph has to go through this point and this point. Of course, you see that I did make it go through those points, but let's see how it works. Okay. So, first thing we do is find the zeros of the numerator, then find the zeros of the denominator. Okay, I didn't mention the zeros of the denominator. Then we find the y-intercept. Let me explain. Zeros of the function, and this is 0, it can only be 0 if the numerator is 0. If the numerator isn't 0, it doesn't matter what the denominator is, you're not going to get 0. We find the zeros of the denominator. Those are also important, because the zeros of the denominator, if they occur, if they're different than the zeros of the numerator, if a 0 of the denominator is not a 0 of the numerator, then what we're doing, when we get near that 0 of the denominator is going to get very tiny. Okay? This denominator is 0 when x equals negative 6. I didn't write out the calculation of that. I just said, obviously, when x is negative 6, the denominator is 0. And then I said, we're going to get a vertical asymptote at that point, much like the way the 1 over x function approaches the y-axis as an asymptote, up here, down here, or the reciprocal square function approaches the y-axis as an asymptote, positive on both sides. It's going to do one of those two things. Okay? That might be negative on both sides, but it's going to have that behavior. So I draw this vertical dotted line that's kind of reminiscent of the way, and the function approaches that dotted line in a way that's sort of reminiscent of the way the reciprocal function approaches the y-axis. Now, why does it approach this way? Because if x is very close to negative 6, then x plus 6 is going to be very close to 0, which means it's going to be really tiny. Maybe it's a tiny positive number. If it's on this side of the x equals 6, negative 6 line, it'll be positive. Or maybe it's a negative number. If it's on this side, it'll be negative. That's going to divide into x minus 4. Now, if x is close to negative 6, x minus 4 is close to negative 10. So you got this tiny number divided into negative 10. Well, tiny number divided into negative 10 If the tiny number is negative, it's going to give you a really big positive number. When a tiny number goes into a number that isn't tiny, you get something big. Okay? Okay, on this side of the x equals negative 6 line, x plus 6 is positive. Like if x is negative 5, that's not all that close to negative 6. But if it's negative 5, then negative 5 plus 6 is positive 1. Anywhere on the right, to the right of this vertical line, the denominator is going to be positive. So you're going to get a tinier and tinier positive number as x gets closer and closer to negative 6. It goes into negative 10. So you're going to get a big number, but it's going to be negative because it's a negative divided by a positive. So the graph is going to go like this. On the other side, the tiny number is going to be positive, is going to be negative. It's going to go into something close to negative 10. It's going to give you a big positive, which the graph is going to come down like this. Now there's something going on with this graph that I didn't explain here. I'll explain in a minute. When x starts getting big, y starts getting close to 1. I use the example, if x is 1,000, x minus 4 is 1,000 minus 4, which is 996. X plus 6 is 1,006. Now, here's 1,000. Where's 1,006? It's very tiny distance above here. Okay, there's almost no distance at all. And where is 996? It's a little below 1,000. So you got a number that's here divided by a number that's here. They're almost equal. The result is almost 1. So when you have big values of x, whether they're positive or negative, you're going to get results that are close to y equals 1. So when I draw the graph, I draw it so it goes through this point and has an asymptote here. Then it comes up through here, but it has to level off, so it's asymptotic to y equals 1. On this side, it's kind of simpler. It's got to be way up here, and it's got to come down toward 1 down here. Okay, now I haven't drawn it very well to scale, but those are going to be the characteristics of the graph. Okay, well, I say a lot of the same things here. I'll put a little terminology on it. And most of it's worth saying twice because you're not necessarily used to it. Okay, y equals x minus 4 over x plus 6. Y equals 0 when the numerator is 0. So x equals negative 4 is a 0. Graph passes through the point 4 is 0, the x-intercept. The y-intercept occurs when x equals 0. You just plug 0 in for x and you get negative 2/3, so there's your y-intercept. And I've got that on this graph too that looks a lot like the other one. Okay, the denominator is 0 when x plus 6 equals 0. Solve that easily. X equals negative 6. So the denominator is 0 when x equals negative 6, as we saw. That's going to give you a vertical asymptote for the reasons we just talked about. The reasons for this y equals 1, I want to say a little more about that. The far run behavior, that's one term for what happens if you go way out that way or way out this way on the axis, the x-axis. You can call it the far run behavior. You can call it the end behavior. There are probably other names that I'm not thinking of right now. I don't even know what name you've seen in your problems, but it's probably one of these two. But either, whatever it's called, it's what happens if x is really big, a really big positive or negative number. Okay, so it's the answer to the question, what happens if x is really big, positive, or negative? Well, if x is really big, then this is really close to 1. And again, use the example. If x is 1,000, then you're talking about 996 over 1,006. 996 is this big, 1,006 is about this big. You can't even see the difference very, very easily. You can't even move your hand that little. So you have equal numerator and denominator, meaning that your quotient is nearly 1. If x is a big negative number, same thing. So the graph approaches y equals 1, and this looks just like what you saw before. So there's a graph of y equals x minus 4 over x plus 6. Now there's the shape of the graph in this region that's not totally clear. Does it come through this? Does it then, can it dip down and go back up before it levels off? Just how does it behave in this interim? And you need calculus to analyze that. There's no sane way that I can think of you can analyze it without using calculus. Doesn't mean there isn't one. Okay, so there it is.